Did you know that the same metal used in weapons that once changed the course of war, from supersonic jets to deep-diving submarines, is also inside the phone you're holding? That metal is titanium, one of the strongest and most resilient materials ever mastered by humans. Although fairly common in the Earth's crust, titanium rarely exists in pure form. Instead, it lies hidden in hard minerals like ilmenite and rutile, making extraction extremely difficult. To bring it into usable form, the ore must be crushed, refined multiple times, and heated at extreme temperatures. Only after passing through each of these demanding stages does titanium emerge as a dull, silver block, light yet remarkably tough, able to withstand seawater, extreme heat, and relentless corrosion. This is more than a story of metallurgy. It's proof of humanity's drive to expand the limits of what is possible. Stay with us as we follow the journey of titanium, an element as steadfast as it is untamable, and uncover how it has finally been conquered. Titanium's role in modern civilization. Titanium has moved far beyond being just a chemical element. It has become the material capital of our civilization. Its true value lies in unlocking what was once impossible: lighter yet stronger aircraft, corrosion-resistant submarines, and medical implants that can last a lifetime. In this way, titanium not only fuels billion-dollar industries, but also redefines safety, health, and technological progress, cementing its role as a driver of advancement. Even so, titanium isn't always the ultimate choice. Its high extraction and processing costs often push industries to favor aluminum or steel, materials that are cheaper and easier to produce. Even Apple, which once positioned titanium as the hallmark of premium design in the iPhone Pro, is now reportedly considering a return to aluminum for both economic and environmental reasons. This raises an important debate. Is titanium truly worth pursuing at any cost, or should it be reserved only for fields that genuinely require its exceptional strengths? Share your perspective. The best comment will be pinned. Titanium ore mining and beneficiation process. The process of extracting titanium begins with surveying and mapping deposits rich in ilmenite or rutile. These two minerals contain the highest concentrations of titanium oxide and are typically found in coastal sand dunes or buried deep within ancient rock layers. In coastal placer deposits, large-scale hydraulic pumps blast powerful streams of water into sandbanks to loosen the ore grains. The water not only washes away impurities, but also exploits density differences. The heavier titanium-rich particles quickly settle, while lighter sand is carried off. The resulting slurry is then channeled through pipes or flumes into a primary separation station, greatly reducing the volume that needs to be moved by heavy machinery. For inland deposits, the approach is different. Heavy excavators strip away the overburden to reach the ore body directly, after which specialized trucks haul the raw material out. At the stockyard, the ore is screened and washed to remove soil and gravel before being delivered to processing plants. Whether from coastal placers or inland mines, the common thread is the sheer mass of material that must be shifted and the enormous amounts of water consumed, factors that make titanium mining as much an environmental management challenge as it is a technical one. Once the ore has been extracted, it is crushed into smaller fragments and fed into a series of separation processes. Gravity separation isolates the heavy titanium-bearing particles. Magnetic separation removes iron-rich minerals, and flotation eliminates silica along with other light impurities. Each stage acts like peeling away successive layers of armor, leaving behind only the concentrated ore with a titanium dioxide content high enough for industrial use. This marks the close of the mining phase, where a mass of dull reddish-gray sand is gradually transformed into a strategic raw material ready to begin its next journey. Kroll process, from ore to titanium sponge.
Once the titanium concentrate has been enriched, it is transported to metallurgical plants for the decisive stage, transforming mineral ore into metal. The first step is converting the ore into an intermediate compound. Inside sealed furnaces at extreme temperatures, the ore reacts with chlorine gas and carbon, producing a liquid compound that is easier to handle. This solution is then filtered and distilled repeatedly to remove residual impurities like iron or manganese, since even trace amounts can undermine titanium's remarkable strength. When the intermediate compound reaches the required purity, it is introduced into massive steel reactors. There, it reacts with a stronger metal, usually magnesium or sodium, under intense heat and tightly controlled conditions. Over the course of many hours, titanium gradually precipitates, forming spongy deposits that cling to the walls of the reactor. What emerges is not a gleaming ingot, but porous titanium sponge, gray-silver in color, rough in texture, and riddled with tiny voids like a honeycomb. After the reaction ends, the reactor is cooled and opened. The coarse sponge blocks are removed, broken into smaller chunks, and washed to eliminate residual salts. This is the very first appearance, still brittle and impure, not yet ready for practical use, but representing a turning point. From an anonymous ore buried deep underground, titanium has finally taken shape as a real metal, poised for the next stage of refinement. Vacuum arc remelting stage. When the Kroll reactor is opened, the raw titanium sponge emerges, its silver-gray surface rough and uneven, still coated with residual salts. The first step is breaking it down. The sponge block is cut into smaller chunks, both for easier handling and to remove the outer salt layer. These fragments are then washed in a specialized solution to dissolve magnesium chloride and other lingering impurities. Once cleaned, they are carefully dried, yielding a pure titanium sponge. The purified titanium is then grounded and graded before being compressed into solid blocks known as titanium electrodes. This prepares the material for the most advanced stage of refinement, vacuum arc remelting. Inside a VAR furnace, the titanium electrode is positioned vertically above a water-cooled copper crucible. As a powerful current strikes, an intense electric arc ignites, melting the titanium layer by layer. Droplets of molten metal fall to the bottom, gradually consolidating into a dense ingot of titanium, uniform, highly pure, and ready for use in industries where strength and reliability are paramount. Forming and precision CNC machining. Fresh out of the furnace, the refined titanium ingot still glows red-hot, with its surface temperature soaring above 1832 degrees Fahrenheit. In this state, the metal is far more malleable, making it ready for the first stage of shaping. A massive robotic arm clamps onto the multi-ton ingot and transfers it into a hydraulic press. Here, giant pistons descend with crushing force, each strike echoing like thunder. Under this immense pressure, the rough cylindrical block begins to transform. Its surfaces are flattened, its length stretched, and its shape made more uniform. Just as important, the forging process densifies the internal structure, eliminating the tiny voids left from casting and realigning the crystalline grains, giving the titanium greater mechanical strength. Through repeated pressing cycles, the glowing ingot gradually becomes a precisely formed billet, consistent in quality and shaped for the next stage of rolling, forging, or precision machining. This marks a pivotal moment when titanium leaves behind its raw cast form and enters its life as a true industrial material. Once titanium has been rolled into standardized billets, the stage of mechanical machining begins. The ingots are first cut and ground to remove the oxidized layer formed during refining. Sparks fly beneath the grinding wheels. Every millimeter of excess metal is stripped away, leaving behind a flat, clean surface ready for precise processing. Next, the titanium moves to industrial lathes and milling machines. Large blocks are cut down into smaller product-ready forms. Because titanium is exceptionally hard and retains heat, the entire operation relies on continuous cooling systems that protect the cutting tools and prevent the metal from warping. The critical step is CNC machining, where computer-guided precision comes into play. On the CNC table, titanium is firmly clamped in place, while high-speed cutters follow a pre-programmed path. This enables turning, milling, drilling, and engraving to be performed on titanium, despite its reputation for being notoriously difficult to machine, with tolerances measured in mere thousandths of a millimeter. It is through CNC that titanium becomes the core of high-demand components, from jet engine turbine blades to submarine hulls to artificial bone joints in medicine. Each stage of machining reflects both the power of modern machinery and the tight oversight of skilled operators. The result is highly accurate titanium, semi-finished parts, ready to serve some of the most demanding
Industrial and technological fields. Titanium bar packaging and storage. For titanium bars, once rolling and machining are completed to specification, they are bundled together, ranging from a few dozen to several hundred pieces, depending on size. Each bundle is tightly secured with steel straps, then wrapped in plastic or oil paper to protect against moisture and prevent scratches during transport. At both ends of the bars, manufacturers print or attach identification tags with detailed information, alloy grade, dimensions, batch number, and weight. The bundles are then replaced on wooden pallets or steel frames and firmly fastened with industrial strapping. This method of packaging not only shields the titanium from environmental exposure, but also ensures efficient handling, loading, and storage. From aerospace factories to precision engineering workshops and chemical plants, this careful preparation guarantees that the titanium arrives ready for its next stage of use. If titanium is often called a strategic metal reserve for fields that demand extreme durability and resistance to harsh environments, from jet engine turbine blades and submarine hulls to artificial bone implants, then steel stands as the material backbone of everyday life. Titanium is scarce, difficult to refine, and expensive, while steel can be produced in billions of tons each year, becoming the skeleton of human infrastructure. Towering skyscrapers, bridges spanning rivers, railroads, and vehicles of every kind. In other words, titanium paves the way for cutting-edge technology, while steel sustains the rhythm of global industry. The making of steel begins with the extraction of iron ore, the primary raw material. Massive open-pit mines in Australia, Brazil, India, and China account for much of the world's production. Here, giant excavators and haul trucks weighing hundreds of tons work non-stop, stripping away layers of earth and rock to uncover ore bodies. The most common ores are hematite, with its reddish-brown color, and magnetite, with its black magnetic character. Their iron content can range from 30% to more than 60%. Once mined, the raw ore is transported to processing plants. There it is crushed by jaw crushers and ball mills, then screened to separate iron-rich particles from unwanted rock. Processing often includes magnetic separation, taking advantage of magnetite's natural magnetism, or flotation to improve the purity of hematite for efficient smelting. Finally, the concentrated ore is agglomerated into small lumps through pelletizing or sintering, making it easier to feed into a blast furnace. Round pellets a few centimeters across are shaped from fine ore powder mixed with binders, then lightly baked to achieve mechanical strength. This form not only improves handling and transport, but also ensures good airflow inside the furnace, allowing the chemical reactions of steelmaking to proceed more efficiently. The pig iron is then transferred into either a basic oxygen furnace, BOF, or an electric arc furnace, EAF. There,
Pure oxygen or powerful electrical currents burn away excess carbon and remove unwanted elements like sulfur and phosphorus. Through this refining step, the pig iron is transformed into liquid steel, with its carbon content adjusted to usable levels. Next comes continuous casting. The liquid steel is poured into water-cooled molds, where it gradually solidifies into semi-finished shapes, square billets, flat slabs, or round blooms, each destined for different applications. The final stage is hot rolling and cold rolling. Reheated steel passes through massive rolling mills, where pressure and heat reshape it into countless forms: ribbed rebar for construction, large plates for shipbuilding and automotive manufacturing, and coiled sheets for machinery and engineering. This is the point where steel moves from raw material to universal product, integrated into every facet of industry and daily life. Conclusion. From dull gray ore deposits rich in ilmenite or rutile, titanium undergoes a grueling journey: crushed, refined, reduced to sponge, and then purified in vacuum arc furnaces until it becomes a gleaming ingot. Next, through massive presses, rolling mills, and CNC machines, precise to 1/1000th of a millimeter, titanium is shaped into flawless semi-finished forms. From there, it enters the realms of aerospace, defense, medicine, and technology, fields where no ordinary material can take its place. This journey reveals that titanium is not just an element, but a symbol of humanity's drive to push boundaries. Every titanium product is a snapshot of technological history, a material that resists salt water, extreme heat, and crushing pressure, yet remains light enough to fly and strong enough to endure decades of use. Titanium has helped shape the face of modern civilization, standing as proof that from raw minerals, humanity can forge achievements that reach both the skies and the depths of the ocean. If you'd like to keep exploring the secrets of other strategic metals, from how they're mined and refined to how they appear in everyday life, hit subscribe, turn on notifications, and leave a comment. We'll take you deeper into the world where science and technology meet matter, creating the very marvels we live with today.